Hey, this is Horner, and these are the lenses, telescopes, and magnifying glasses problems. So we have the first one. Harold and Roland find a discarded plastic lens lying on the beach. The boys discuss what they've learned in physics last semester, and they have to argue whether or not that lens is converging or diverging. When they look through it, they do notice that the objects are inverted. And so because they're inverted, for letter B, we know that the only way they can be inverted is if we have a converging lens. So for letter B, that should be converging. If the object is sitting 25 centimeters in front of the lens and forms an image 20 centimeters behind, they want to know what is the focal length of the lens. So for this one, it's pretty easy to do. We're just going to do 1 over f is equal to 1 over do plus 1 over di. In this type of lens, everything is where it's supposed to be. So the object distance, so it says the object is 25 centimeters in front, we'll put 25 there. And then the image is behind the lens, which is where it should be, so it's positive, so that's 1 over 20. If you go through and do the fractions for the math, you're going to end up with 0.09. And that 0.09, remember, is 1 over f. And so now we've got to flip both sides, so f would be equal to 1 over 0.09, and then that makes your focal length 11.1 centimeters. So that is the first problem. Let's go ahead and take a look at the second problem. It says Sadie looks at her friend's face through a diverging lens. They want to know, is it real or virtual? And remember, for diverging lenses, we always have a virtual image. Next thing they want us to do is, if her friend's face is 50 centimeters from the lens and it forms an image distance of 20, what is the focal length? Well, because it's a diverging lens, the DI here is always negative. So this is negative 20 centimeters, and our DO here is always positive regardless of the lens and the situation. So it would be 50 positive centimeters. We need to plug everything into our equation now. So this is 1 over f is equal to 1 over do plus 1 over di. And we do remember with the diverging lens that the focal length here, when we're done, should be negative. So let's find out if that happens or not. So this is going to be 1 over 50 plus 1 over, and don't forget this is negative, oops, I wrote a 2 instead of a negative 20. And if you do your math, you're going to end up with a value of negative 0.3, but that's for 1 over f. We want f, so f is equal to 1 over negative 0.3. Our answer is negative, which is good, and the value here is 33.3 centimeters. For the next problem, which is number 3, it says Giorgio is clicking shots of fashion model Nadine. She walks across the studio. The camera has a lens with a focal length of positive 0.05. So this one we know this has got to be a converging lens. They want to know, how far back must the detector be placed, located when Nadine is 3 meters from the camera. So we've got our lady and we have our camera. And inside that camera, there is a detector. So the light goes into the camera, and then there is a distance from that lens back to the image, and that is our DI. Our distance from the lady up to the camera, remember, is our DO. So here, she is 3 meters from the camera, and the camera has a focal length equals 2.05 meters. So now what we need to do is find out what is our DI. That's essentially what we're looking for here. So 1 over f is equal to 1 over DO plus 1 over DI. And now what we're going to do is rearrange the equation for DI. So 1 over DI is equal to 1 over f minus 1 over DO. Let's plug everything in. So this would be 1 over 0.05 minus 1 over 3. And so here we end up with 19.7, but that, remember, is 1 over di. So di here is equal to 1 over 19.7, and that gives us a 0.0508 meter distance to the image, and that's good because that's about 5 centimeters, and the camera can make that without any problem at all. They want to know, should the lens be moved out or in as Nadine approaches closer to the photographer? And it should be moved out. It should be moved out by the way that the DI and the DO work. And that is number 3. So let's go ahead and take a look at the next problem. Number 4, Dr. Wasserman is showing slides to his biology class. They are positioned 15.5 centimeters from the projector lens that has a focal length of 15. Where should the screen be placed to produce the clearest image? So here we've got some sort of lens. We have a slide. So these are the old slides that they used to have in slide projectors, and you would have a light. Okay, so here we've got light, and that light is shining through, and then the image is then transferred to a screen over here on the other side, and then you would see whatever it is that the biology teacher is putting there. So let's go ahead and do our image stuff here. Do notice the focal length is positive, so it is a converging mirror that looks like this. And the slides are 15.5 centimeters from the projector, so that is our DO. We want to know what is the DI. So let's go ahead and write our equation. Here we've rearranged it already. 1 over DI is equal to 1 over F minus 1 over DO. Our F here is 15. And then we're going to subtract 1 over 15.5 for the position of the slides in that projector. This ends up being 2.15, and we know that's 1 over DI. So if we want DI, we're going to take 1 over 2.15, and we end up then with an answer of 465 centimeters. And that would be the position of the screen, or about 4.65 meters from the screen. For the next problem, this is number 5. Marlin is out on a safari, looks through his telescope. He does spot a giraffe in the distance. He has an objective lens of 40 centimeters and an eyepiece of 2 centimeters. So the objective here is 40 and the eyepiece is 2. They want to know what's the magnification. So remember, magnification is several things. It's di, do, it's hi, ho, and then it's also pho, phi. And so for the one that we're doing, we notice we have an objective lens, so that's the focal length of the objective lens, and the eyepiece. So we're not going to use these two, we are going to use this one. The focal length of the objective is 40, and of the eyepiece is 2. So now we see that simply it's magnified by 20 times. For letter B, they want to know how large is the image formed by the telescope if the giraffe appears to be 1.5 centimeters high to the naked eye. So here we know that magnification is equal to HI over HO. And we need to solve for HI. So HI is equal to magnification times HO. Our magnification is 20. The height of the image is 1.5. And so when you multiply those two together, it appears to be 30 centimeters in terms of the image height. For the next one, which is number 6, we have Emilio, an entomologist, studying a millipede hole that is held behind a magnifying glass. The focal length here is 2. We know that the near point is 25, so we want to find what is the angular magnification. So remember, big M is angular magnification, and it's just the near point, so NP, which is 25 for this person, and we divide that by that focal length. So near point is 25, angular magnification, we want that, so we're going to divide by the focal length, and 25 divided by 2 gives us an image that is 12.5 times bigger. Does Emilio have to bring the magnifying glass closer to or further from the millipede to make it larger? And to make it larger, we do want to move it further from. Okay, so farther from. The next problem that we have is number 7. It says, Mr. Crabtree, a jeweler, looks through a jeweler's loop. So that's just a small magnifying glass that is attached to his glasses. In order to read the engraving on a pewter bowl, the loop has a focal length of 3 centimeters. If his near point is 24, what is the angular magnification? So here we go again. The near point divided by the focal length. Our near point here is 24 centimeters. 24 centimeters divided by the 3 centimeter focal length. And so we see that it is simply just 8 times magnification. And that is number 7. Let's go ahead and take a look at number 8. It says there's a copy machine that is set to reduce the size of a printed material by 50%. When the print is regular size, both the image and the object distance are 16. If the lens is moved to 24 centimeters from the object, how large is the new image distance? To do this one, we're going to have to do a couple things. First thing we need to do is let's go through and find the focal length. So we're going to say 1 over f is equal to 1 over the object distance plus 1 over the image distance. So that's equal to 1 over 16, so that's our object distance. And we need to add that to 1 over, and then we're going to do 16 again because that is also the image distance. So it says both the object and the image distance, so that's why they are the same. That's equal to 0.125, but that's 1 over f, so f would just be the inverse of that, so 1 divided by that, and it would be 8 centimeters. The next thing we need to do is let's find out what is the new image distance, so that'd be 1 over di is equal to 1 over f minus 1 over do. That's equal to 1 over 8. And then we're going to take that and subtract 1 over, 24. So now we have that. We're going to do our math. We get 0.0833, but that's 1 over di. So di is just equal to 1 over 0.0833. And so we end up with a di of 12 centimeters. That is the new image distance itself. For number 9, it says the average human normal eye forms an image on the retina of a distance about 0.024 meters from the lens, or 2.4 centimeters. How much must the focal length of the lens change in order to accommodate an object move from 10 meters to 0.25 meters? So this change really is in focal length is accomplished by the little tiny muscles in the eye called the ciliary muscles. They actually stretch and they relax the lens as it does that. So let's do this at 10 meters. We know that the focal length is going to be 1 over f, and that's equal to 1 over do plus 1 over di. They gave us a do here of 10, so I'm going to put 1 over 10. Plus, now I'm going to do 1 over di, and that's the image distance, which is 0.024. When I do the math, I end up with 41.8, but remember, that's 1 over f, so f is going to be equal to 1 over 41.8, and I end up with 0.0239. Let's do the same thing now. We have to do it at 0.250 meters. And so we will do 1 over f again is equal to 1 over do, which is 0.25, plus 1 over di, which is 0.024 again. And that is equal to 45.7. We need to find the focal length, so that would be 1 over 45.7, so we get 0.0219 meters. So the change in that focal length is equal to 2.39 centimeters minus 2.19 centimeters. So the focal length change there is about 0.2 centimeters. As you get older, your lens gets a little bit thicker. It's really hard for the ciliary muscles to move it, and you end up having to wear bifocals. That one is number 9. Let's go ahead and take a look at number 10. Cindy is lying on the beach, and this is our last one. So Cindy is lying on the beach, focusing her camera on a friend standing 5 meters away. Her camera has a focal length of 5 centimeters. They want to know where must Cindy position the camera lens relative to the detector to get the sharpest focus. So for this one, we want 1 over di, and that should be equal to 1 over di here is equal to 1 over f minus 1 over do. At this point now we're going to do 1 over the focal length, and that is 5 centimeters. And that is minus 1 over the distance to the object. Notice this is 5 meters. You can't put 5 again. We have to put it in centimeters. So this is going to be 500 centimeters. And we end up with a number here of 0.198. That is 1 over di. So to get the di, I just need to take 1 over 0.198. And if I do that, I get 5.05 centimeters. For letter B, it says what type of lens must our camera have, and it has to be converging, and it's converging because it's the only type of lens that can project an image. So this one can project an image. The diverging lenses can't. You can see the image, but you cannot project that image on a piece of paper. And that is the end of this problem set.